Now to calculate the value of n of d1 and n of d2, we need to create some space. I've actually gone ahead and added some rows here, added some rows here, so that we have more space to play with. And what I'm going to do now is calculate n of d1 and n of d2. Again, Excel comes to our rescue and we use the function norm s dist for d1 and norm s dist for d2. There you go. Sorry. Norm s dist for d2. So now you can see that there is a difference in probabilities nd1 and nd2. We've already done what nd1 and nd2 mean in a previous part of our course. So now let's compare the value of d2. What is nd2? nd2 is the value that st is greater than x. So the true value for nd2 is 0.335635. The value that we have here with our friend the Monte Carlo simulator is 0.349. Okay, now the value of the call premium, the value of the call option is our old friend, the formula for a call option. We have the Excel spreadsheet. There we go. Let's just cut and paste this formula from there to here. Put it back into a sheet. This will take some space, but we can reduce it, or as Harry Potter would say, reducto. So let's do a reducto on the sheet. There you go. So that's the formula for the calculation of a call option, which is simply SND1 minus XE minus R T minus D ND2. So an asset or nothing option, short less a cash or nothing option. And if I plug this formula in here, S is here, that's 10 into N of D1, my friend here, minus X, which is the strike, into the PV factor for the whole time, which is here, into n of d2 that I've calculated here. There we go. So that's the value of a call option. Now the true value of a call option based on the Black Scholes equation is 0.860629. The value that we have is 0.8521, which is not that bad. Finally, the value of the put option is simply you flip this equation, flip it around. So this becomes xe minus rt minus t n minus d2 minus Sn minus d1. So what you're doing is, for a call option, you're interested in the probability of St greater than x. For a put option, you're interested in the probability that St is less than x. So if I flip this, I'm saying x is my friend here, x into PV factor for the entire time, t into n. Oh, so we don't have n minus d1 and n minus d2, which means we have to take one quick step back. Now to calculate n of n minus d1, need to explain a simple concept. N minus d1 is the same as 1 minus n d1, and n of minus d2 is simply 1 minus n d2. Right? So you flip the probabilities. This is the probability that st is greater than x. This is the probability that st is greater than x. What is the probability that st would be less than x? It's 1 minus this number. And same thing goes over here. So if I, now that I have n minus d1 and n minus d2, I now do again x, my friend here, into the PV factor for the period, into n of minus d2 here, minus s into n of minus d1, which is here. Right? So the value of a value of a put option based on this formula and this calculation is 1.718. Our value is 1.726. So we've not done that bad. If I calculate the error term, if I use these as my primary drivers, I'm saying the error here, these are my results, here's my error. The error here is, where is the error? The error here would be, for st is greater than x, the true value is this minus this. That's the error. The error here would be value of the call option, which is 0.8609 minus 0.8521 here, and the error here would be where is the value? 1.71 minus this 1.726. Right. So now just in terms of convention, if this error is negative, all I'm saying is that the value that I'm getting from the the calculator, the Monte Carlo simulator is overstating. The true value is 0.335635. The value that I get from here is 0.349, so you're overstating. And if it's negative, then I'm understating, right? And the overall error is 0.01. So if I reflect the error in terms of percentage terms, how would you reflect the error in terms of percentage terms? These are absolute values. Right? In terms, if you were to express the error in percentage terms, percentage error, you would simply take this and divide it by the number that you calculate. Now, you can divide it by this number, or you can divide it, since you know the true value, you can simply divide it by n of t2. So that's 4%, and for the call option, it's this divided by, it's going to be possibly lower, so that's the call premium, 1%, and here is also. Alright, so now let's track and take a look at the error. So the error for the Monte Carlo simulator, as defined by our calculations, is about, so this you can translate into percentage. You can simply apply the percentage factor and say overstatement by 4%, understatement by 1%, and overstatement by 0.5%. Now if you update this, remember before we came here and we switched this, we turned calculations off. You can now see, when I saved the sheet, Excel actually went ahead and updated all the numbers. The error is about 5.8% for ST is greater than X for the probability, about minus 2%, 2.5% for call, and about 2.6% for the put. Let's see as we walk through how much changing this model has helped. This won't work because I've switched this to manual. Let me bring this back to automatic, and we get, okay, so now when it calculates, so 5%, 12%, and 1%. That's not good. Next, 1.19%, 8.5%, 1.7%. That's still not good. Once more, 2, 11, 3, not good. 3, 3, and 2, not good. Now, in Monte Carlo simulation, there is a very simple basic ground rule, and that basic ground rule is that the error should reduce by the square root of iteration. So, right now we're doing about 1,000 iterations. Take the square root of that, and that's the number that will reduce the error by. So, if I say, if I'm doing 1, so let's say 10, that's what we did. Then we did, after 10 we did 100, after 100 we did 1000, and if you allow me, and if my laptop actually manages to survive, we'll see if we can extend this to 10,000 simulations. It'll be a little slow, so we'll have to be a little patient, but we're saying the error is reducing by this divided by the square root of n. And if I allow me to extend this, because things are going to upset. So I'm going to take this and divide by square root. So if that's the error, as I increase this number, that's the impact. So let's see if this helps. Let's see if we can reduce the error. Right now, if you look at the error, it's about shuttling between 2%, 3%, and 1% to 2.27, there you go, 2.27, 3.99, 1.15. So let's see if we take it to 10,000 simulations. Now, as I advised earlier, first thing that we have to do is to make sure that we save our work, and we will now repeat everything that we've done and extend it to 10,000 simulations. We have 1,000 simulations. Let's see if we can take this sheet all the way down to 10,000, and this is going to be maybe a lot more awkward. So quickly running this through to, let's do 5,000 rather than doing 10,000. Let's do 5,000 simulations. Save us a bit more time. Yeah, there you go. So that's 5,000 simulations, and we are going back 5,000, 5,000 simulations. Right, that's 5,000 simulations. For reference, remember the cells 5,009. 5,009 is our reference cell. Let's run this quickly one more time. Press data, what if analysis, table, blank column, pick a blank input cell, press OK, and there we go. So when we did 1000 simulation, it took about 8 to 10 seconds. We'll quickly find out how long it takes now when we calculate these numbers. Whoa. Okay. So for 5000 simulations, I press 1. The first error estimate is about 4%, 7%, and 0.35%. I press it now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 25 seconds. So what we've done is we've increased the number by 5 times, from 1000 simulations to 5000 simulations. The time has gone up from 8 to 10 seconds to about 25 seconds. So while we've increased the number of simulations to about 5,000, because we had a fair bit of excess capacity on the computing side, for 5,000 simulations is taking about 25 seconds to run on this laptop. Now on this laptop, the error as of now is now about 1.38%, minus 3%, and 5.38%. If you look at the results, ST greater than X is now only 0.33. Call is 0.88. Put is 1.626. If I press this again one more time, I want to see how much variation do I get, or will I get, when I go from one iteration to the next iteration. And from a calculation point of view, you can see that this went from 0.33 to 0.36. This has gone from 0.9. Oh yes, so there is a mistake that we made. Can you tell me what is the mistake? Can you tell me why these, despite the fact that we've gone from 1000 simulation to 5000 simulations, why is it that these numbers are not making sense? And the reason, I'll tell you this, the reason why these numbers are not making sense is while we've gone out and upgraded the grid, we've made one very fundamental, very common mistake that I make all the time, and there's a good likelihood that you'll possibly make all the time, and that mistake is that when you update this grid, you also have to update our friends here, the averages here. So this needs to read 5000, not 1000. And it's only when you take it to 5000, only then will this get updated properly and appropriately. If you don't do this, then this will not work. So now we should see a fairly significant reduction, right? Because now, as far as our calculations are concerned, now you're running the full 5000 and you're using the full 5000 also for your results. Previously, the error term that we were looking at were running in the range of about 3%. We expect them to get down to about 1.5% as per this table, or about in that range, about between 3% to about 1.5%. The error that we see is 1.6, 2.0, 1.37%, 0.8787 versus 0.8606 for the call, 1.69 versus 1.71 for the put, and 0.3410 for the probability that ST is greater than X. Come back here, update it again. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, 1, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, 2, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, 3, 10, 9, 8, 7, 6, 5, 4. Okay, good. So about 35 seconds. One possibility could be because we've now updated the average function to go all the way up to 5,000 calculations rather than the 1,000 that we were doing earlier. So now 0.3254, 0.8378, 1.737. One last and final time to see how much, but you can see the trend. You can see that when we went from 10 to 100, from 100 to 1000, from 1000 to 5000, based on the analysis that we're seeing here, the accuracy is improving, the error is reducing, not as much as we'd like to, that we'd hope to, that we'd want to, but it's certainly reducing. The expected error based on this table that we were working with earlier is also supposedly in this range. and the numbers that we're seeing are also showing. Yeah, there you go. So you expect to see about 1.4%, and you're seeing a number between about 2% or so, and that could be for a wide variety of reasons. So our objective now that we've done this, is to quickly review how have we gotten to this point. What we've done is, we've built a Monte Carlo simulator. We built this Monte Carlo simulator by taking these inputs, using a random number, applying the normal transform on it, so that we have a normally distributed random number, calculating a path, simulating that path. There's a path, simulating a path, calculating results, calculating numbers, calculating the stable. And then when we are not sure about the accuracy of our analysis, we actually went back to the closed form formula, the closed form solution for the Black Scholes equation that gave us the value of a call premium and a put premium, and we use that to calculate and estimate the error. And the concept that we are trying to highlight and illustrate here was, how does error reduce as you increase the number of iterations. And you can see that this table here and this reduction here are closely following each other. If I take this from 5,000 to 50,000 simulations, for instance, you can, so now to reduce error by 1/3, you actually have to raise this by 10 times. That's the reduction. So if you look at the number of iterations here, from reduce the error by third, you actually had to increase it by 10 times. Reduce it by a third, increase it by 10 times. Increase it by 5 times. Reduce it by half, increase it by 5 times. Reduce it by a third again. So that's the square root of n. That's the concept. That's where this number is coming from. So this finishes and wraps up our session on building a Monte Carlo simulator. I hope you've enjoyed what we've done. Once again, the idea was to get to a point where we could simulate a price path and use that price path to calculate values for a European and European call and a European put contract. Then compare the prices that we generated with exact numbers, exact premiums as calculated by the Black Scholes equation, and then see that as we increase the number of iterations, what was the actual reduction in the error term. In additional related courses on Monte Carlo simulation as well as derivative pricing, we will take a look at how we can reduce the variance, increase the stability, and improve the convergence in this model by evaluating antithetic sampling. That's one area. The other area that we have to work at is, how do you take the sheet that you just built for a vanilla contract and extend it so that it can price exotic contracts and exotic products. That's number 2. And third and final piece is, what about Greeks? What about sensitivities? Can we do anything to calculate delta, gamma, vega, theta, and rho? The option price sensitivities based on the change in the price of the underlying, change in the price of change in volatility, change in the interest rate, change in time to maturity. Is there a mechanism for us to calculate these from the sheet that we built here? These are additional components and modules that we'll cover at a later date. I hope you've enjoyed yourself. This is Jawad Fareed signing off for financetrainingcourses.com. Thank you very much for your time.